the number of queries are growing up exponentially, so is the power consumption need. So I'll just take you through the different generations of the server power tree. So starting with the generation 1, this is was there for the longest time. I think it is still very relevant. This you can see is where you have a three-phase AC at, let's say, the grid level or at the infrastructure level, which comes in, and then we have a PDU here, which converts it into or rather which switches it into a single phase AC, which eventually goes into the server rack. Now at the server rack itself, there are multiple blades, as you can see, and each blade has this AC to DC conversion where it takes in the one phase AC, which is 240 volt, 208 volt AC, and converts it into a 12 volt DC power, right? So you have a kind of an onboard AC to DC conversion, and then the 12 volt is further down converted by a VR stage, or the voltage regulator stage, to give it to a server, which is, let's say, at 1 volt or 0.8 volts or some power level like that. So yeah, I think this is how the conversion works. For battery backup or for, let's say, power backup, we end up using an UPS, and that has some inherent challenges, like there is a DC to AC from the battery and then back again to AC to DC conversion that happens to actually utilize that UPS power, which adds, those two conversions adds a little more inefficiency in the power system. So roughly, if you see, the efficiency that we estimate of all the power systems combined is roughly around 80%. So yeah. But now if you switch to the next generation, which is basically the 48 volt data center power architecture, here you see there is a slight change in the way it works, right? Here, each data center rack, as you see, instead of having the complete power conversion happening on board on the server motherboard itself, there is a power shelf that is dedicatedly available on the rack. So now, just taking you through the architecture a little bit. Again, it works off the one phase AC. Now there are cases where it's also working off three phase AC. But essentially, the power shelf, which is dedicatedly present in the server rack, which is separate from the motherboard shelf, that does the AC to DC conversion. So it takes in the one phase or three phase AC, converts it down to a 50 volt DC bus. Now, the question may be made as to why did the second generation choose 48 volt or 50 volt as the architectural choice? So the reason for that is essentially the going from 12 volt to 48 volt, you are almost increasing the voltage by 4 times. Therefore, to deliver the same power, the current will reduce the 4 times, since power is V times I. And as a result of that, the I square R losses that you will end up losing in distribution. So current square into the resistance of all the wires and all the cables that go from one place to another to carry the power, that reduces by almost 16 times, because your I is reducing by 4 times. So your I square for the same R will end up reducing the power loss by 16 times. So that's the reason. And as a result of that, you can increase the amount of power that you can pump because you are able to reduce your losses there from the distribution front. And that's the reason the 50 volt or 48 volt became an architectural choice. A question may be made, why not higher voltage? So 60 volts is where I would say it's adequately safe for humans, and being below 60 volts is where it's adequately safe for humans. So these racks and these blades that go in the racks are all hot swappable by human intervention. So that's the reason with some headroom 48 volt was chosen, because it's safe for human interaction. So coming back to the slides itself, the first stage, the power shelf converts the AC to 50 volt DC, and then that 50 volt or 48 volt DC goes into the server motherboard. There's another down conversion where the IBC subsystem. It's called the intermediate bus converter, which converts the 50 volt down to 12 volt or another intermediate voltage, but 12 volt is the most popular one. And then the 12 volt is further down converted to the core voltage, which just then goes to the uh, to the uh, to the processor itself to do the processing. So IBC is basically a DC to DC converter, which does the conversion at a high efficiency from 48 volt down to 12 volt. The BBU, or the battery backup unit, that is actually a proxy for the UPS now. So if you remember in the previous slide, the UPS was somewhere on the AC side, but now in this case, the power backup is moved closer to the load in the DC side. And here is where there is a DC to DC converter in the battery backup unit, which basically uh, can charge from the mains as well. Like it can charge from the 50 volt DC bus when the power is on, or if the power is interrupted due to some power failure, the BBU actually discharges as well into the bus, and there it's the power source is the battery. So battery which you have charged with the 50 volt bus when the power was on actually discharges very rapidly through the same DC to DC route into the motherboard and make sure that either it sustains the operation for a few minutes or enables safe shutdown. So it can be depending upon what's the context, what's the application here. The BBU can either be used for a safe shutdown or to sustain operations for a few minutes before uh, it shuts down or before the power comes back on. So that's the function of the battery backup unit, and we will talk in more detail about IBC and BBU in the coming slides. I would like to also talk about the Gen 3 architecture, which is really booming right now in terms of conversations. I think the OCP summits of this year and the last year has talked extensively about migrating upwards on the bus from 48 volts to actually going up to 800 volts or plus minus 400 volts. So again, at the high level, the reason to do that is basically to again reduce the I square R losses, because as the GPUs and XPUs, I would just call it XPUs, which is the proxy for CPUs, GPUs, TPUs, as different companies call it. So the XPUs actually are becoming even more power hungry. And even at 48 volts, we are seeing that the distribution losses may be higher for the next gen of XPUs. So as a result of that, the idea is that you need to have a separate sidecar uh, which can do the power AC to DC power conversion, and it will now be a complete three-phase AC system, which will convert down to 800 volts or plus minus 400 volt DC, which will then go to the IT rack. So the sidecar is just the power conversion rack, and an IT rack, which is like a similar rack there. You can see like this is an AC to DC rack, and then this goes to the IT rack, which just has the motherboards. That will then take in that 800 volt or plus minus 400 volt and then do the further processing, right? So that's that. And then what will go on the AC to DC rack is the PSU, or the power supply unit, which does the AC to DC conversion, and the BBU, or the capacitor bank backup unit, which will now be at the higher voltage. It will not, because now the DC bus is at a higher voltage, so it will now support the higher voltage, which may be 400, which may be 800. So the BBU system will change with respect to what voltage it needs to convert now. So earlier it was a 48 volt BBU, now it's a 400 volt BBU. And then as the 400 volt or 800 volt enters the motherboard via the IT rack, that's where there are two levels of conversion, 400 to 48 volt and the 48 volt to 12 volt. And then from the 12 volt onwards, the story is the same, though the power levels are much higher in this case. So yeah. Okay. So TI currently has a major play in most of these power conversion, I would say, sites. Like if I talk about BBU, IBC, AC to DC, PSU, we have our new GaN power stages, which are able to enable these conversions. Like these are GaN FETs integrated with drivers, which are able to help these conversions from happening, or rather enables these conversions to happen via different topologies. So I am today only going to shed some light on the 48 volt and the BBU and the IBC, which is relevant for both Gen 2 and Gen 3 IBC as well. But yeah, there are many reference designs, etc., that we do to tackle the high voltage brick, the three-phase rectifiers, and even the VR stages. So all these are the different power building blocks to deliver the power to the motherboard. Yeah. All right. So wanted to just give that quick introduction to segue into our GaN portfolio. So our GaN portfolio is rapidly growing. One thing that we do is we integrate our driver with our GaN device. So the reason we do that is because it helps you deliver more high density designs. If you have to lay out the driver and the FET separately, and then also sensing circuits around it, like let's say the overcurrent, over temperature protection, the short circuit protection, all of that are extra circuits around it that will just take a little more boardroom. It will lead to a complicated design layout because these are very high density designs. So what the GaN or the TI GaN helps the designers and the layout folks is with that it helps you ease that pressure on the real estate on the board, right? And at the same time delivers all these features with an integrated driver like overcurrent protection, over temperature protection, uh, even like some smart switching features like zero voltage detection, zero current detection for some of the resonant topologies where you need these I would say details, or rather these indications to have a successful conversion of voltage from one level to another. So first of all, just talking about our presence, I think we have a complete grid to gate strategy, right? We go from like the AC power, be it one phase AC or three phase AC. The PSU rectifies it, converts it into DC, be it 48 volt DC if it's Gen 2, or plus minus 400 or 800 volt DC if it's Gen 3, which is adequately supported by a BBU to hold up the power if the main power, there is a main power loss. And that also can have TI designs or TI based designs which can enable either of the voltage levels. Then the DC bus enters the motherboard, and here if it's a 48 volt IBC or a 400 to 48 volt DC to DC module, we have a GaN based design presence or a GaN based designs and engagements with many customers on both these subsystems. And then after that, it gets converted to a lower voltage. It goes to a multi-phase VR, which also we have some silicon-based solutions for. And then it goes to the XPU, as I just mentioned about it. And just talking about the GaN power stages now. So we have power stages available in both high voltage and medium voltage, right? High voltage are 650 volt rated and medium voltage is 100 volt rated. So this enable the power conversion and from in all the subsystems that I showed in the previous slide. So be it the AC to DC subsystem or the DC to DC subsystems like BBU or IBC. So just talking about our the high voltage devices first. These are all 650 volt rated, and RDS on start from 25 milliohm, go all the way up to 70 milliohm for the high power devices, and all the way up to 230 milliohm for the low power devices. All these devices come with an integrated driver with integrated overcurrent, short circuit protection, over temperature protection. So all the protection features and the fault reporting is integrated. Plus, additionally, we have some smart switching features such as zero voltage detection, zero current detection as well, as I just mentioned. We have the devices available in two different packages, TOL and QFN. So TOL is a more industry standard package where we can create like a compatible layout with a discrete TOL GaN FET. So we have one in that package, and then we have a QFN package as well, which is very widely accepted and is available in both bottom side and top side cooling options. So that is another way of like looking at the overall packaging. Coming to our medium voltage devices, we have both half bridge devices and single FET devices. over here. So starting with LMG 3100, which is a single FET device, we have two variants of RDS on release, 1.7 and 4.4 milliohm. So depending on the power level, you can go with either of the RDS ons. Both are pin compatible with each other. This again comes with an integrated driver and level shifter with bootstrap to have a high side supply and drive when you are connecting it in a half bridge. So you don't need to attach an external level shifter and bootstrap. So you actually also reduce the BOM on that aspect when you're doing a half bridge power conversion, which is typically the case in most power conversion topologies that end up getting used. Coming to the 2100 device, we have two RDS on options, 2.6 and 4.4 milliohm. This is an integrated half bridge. So basically, two FETs are integrated with the half bridge driver and the level shifter and bootstrap. And both these devices are actually topside cooled primarily, but if you see, there is a big pad on the bottom side as well, which ensures that you actually effectively get kind of a dual side cooled scenario over here. Okay, so now moving on, yeah, this is the high level summary of why TI GaN works in server power. Uh, I have given glimpses of it in the previous slides and while I was talking, but at the very high level, it is efficiency across subsystems, be it AC to DC or DC to DC stages, and it delivers on all the different parameters that go, like we have the 80 plus titanium standards, the MCRPS standards. So whatever parameters and standards that are out there, we have designs that kind of meet and exceed those standards with our GaN based solutions. We also have a very high power density. Our integration strategy, along with being able to increase the switching frequency with the GaN devices, and truly being able to increase the switching frequency because of integrated GaN devices, as it has no or very less parasitic coupling on the gate loop. We are able to actually deliver really high power density designs. And yeah, the integration, as I have already touched upon, with the gate driver and the smart features always helps in simplifying the design and being able to implement many topologies or different types of topologies with a lot of ease, with all the smart features that is inside. And yeah, we have also options of both top side and bottom side cooling. So depending upon how you want to cool the design, and cooling is definitely a major topic in data centers. We are looking at immersion cooling, liquid cooling, all different types of cooling technologies now coming in. It becomes very important to give the customers or give the designers that flexibility to be able to use top side or bottom side cool devices. All right. So with this, I'll now segue the second half of the presentation into TI GaN and battery backup unit. Feel free to keep posting your questions. We have a moderator who will be looking at it, and we'll make sure that most of your questions are answered either on chat or verbally. So please keep posting your questions here. So yeah, coming to the TI GaN and battery backup unit, or BBU. This is a basic block diagram of a BBU, right? If you see, it's basically, and I'm just tackling the Gen 2 BBU today, which is basically the 48 volt BBU. There are also CBUs at 48 volts. So yeah, it's a BBU slash CBU. CBU is being the capacitor backup unit. So here you see, usually it is a 4-switch buck boost topology, right? So from battery to the bus. See, on the left side is the battery, the right side is the 48 volt bus. So it can charge from the bus if the power is on, or charge the battery from the bus, or the battery can discharge into the bus when the main power is shut off. So typically it's a 4-switch buck boost converter controlled by an MCU or an analog controller. And here is where we use, for the 4-switch, we end up using the TI GaN devices, right? And we have various designs also to prove it, but at the high level, we use our TI GaN devices to do this conversion at a very high frequency and a very high efficiency as well. So overall, the integrated driver, integrated level shifter, and bootstrap helps you in achieving a very, very optimal design. At the same time, you get a lot very low switching loss because of the low figure, very good figure of merit of TI GaN versus, let's say, silicon. And also due to the integration aspect. So due to the integration, what happens is the parasitic coupling, the board level parasitics due to PCB trace, due to common source, due to other like package parasitics, all that get eliminated because our entire gate loop is inside the device since we integrate the driver. So that is that. And then we have in the medium voltage space a lot of new devices coming up with the fault reporting features, the zero voltage detection, ideal diode mode, which will further help you enhance uh, the robustness of the device. And these will come in a similar package, so you don't need to really change your layout. And then it will help you in achieving even high efficiency, high density designs as a result with all the future innovation that we are doing. And this is just to compare the device with a silicon. So typically we see that there is still a lot of silicon based BBU designs that we are competing against. And I've just done a very high level comparison at and you can see the blue bar on both the graphs is TI GaN. The orange bar is silicon at 80 kilohertz. TI GaN is at 200 kilohertz, by the way. And the gray bar is at the same silicon at 200 kilohertz. So typically, because silicon has a high output capacitance, it ends up switching at a fairly low frequency. So that's why we have it at a parity frequency at 200 kilohertz, but we also have it at a lower frequency at 80 kilohertz, which typically is many designs. And as you can see, both in the buck stage or the boost stage, right? If I do a 56 to 51 volt buck or a 44 to 51 volt boost, and 51 volt is just so don't get thrown off by me using 48 volt, 50 volt, 51 volt. These are typically uh, depends on customer to customer which bus voltage they end up using, but it is one of these two, three. There's also the 54 volt. So in the range of 48 to 54 volt, actually it can lie anywhere. So don't get thrown off by that. And it's anyways not a major change, so it's fine. So yeah, 56 to 51 volt. If you see the buck, are the TI GaN device of a similar RDS. Actually, we are using a higher RDS on device. We are comparing it with a 1.5 milliohm device with a 1.7 milliohm TI device and a 1.5 milliohm silicon FET. And still we are able to deliver the best loss performance. Right? You can see our losses are 70%. The silicon losses are 70% higher on buck. And if I talk about just the 80 kilohertz silicon, and 72% roughly higher on boost at the mid load point or at the 50% load point, right? And similarly, if I compare the 200 kilohertz, then the loss numbers will be even more drastic. I think more than double in both cases at 50% load, right? So yeah, I think it's very clear that at the system level your loss savings will be better, especially since you have a battery based system. Each watt that you can squeeze out of the battery is super crucial. So if you just use GaN, you're able to cut your losses by as much as 70%. In cases where you are using it at a low frequency, the silicon at a low frequency, and if it's at a higher frequency, that number will keep going up, the loss saving numbers. So yeah. And just to give you a snap of just the layout level comparison, also we have done a layout of a parallel half bridge, right? And as you can see, we have used our single FET device on the left, the 3100R017, which is already released, and the 5x6 standard GaN FET, standard silicon FETs on the right side with an external driver. And you can see to deliver the same power at a higher efficiency, you are actually having a 60% lower layout size. So you can see the silicon layout is almost 60% higher than the GaN layout. So you're getting a better efficiency, or rather a 70 to 100% better loss performance at a 60% better power density. So it's like a double whammy, I would say, if you have to use that word, and it really helps you in achieving really high efficiency designs with a really high power density. Yeah. And this still doesn't include protection, by the way. So our devices also have scalability to actually offer protection features and smart switching features, etc. With silicon, still don't have the extra circuitry made built in for that. So if you build in that circuitry, this 60% number will look even higher, or the power density number for TI GaN will be even better. So yeah. So we have a few designs that are there. These are all released on ti.com, right? So the first is the PMP23421, uses a digital controller. It's a six-phase design. You can see there are like seven cards. Six cards are for charging, one is for discharging. Sorry, I said the other way around. Six cards are for discharging, one is for charging. And it is based on a C2000 microcontroller using our LMG 3100R017, the same device where we did all the comparisons in the previous slides. So please take a look. You can see that this hits a 99% peak efficiency, and it meets the OCP ORV3 standards, which is one of the standards for the BBU designs. We have another one, PMP23377, which is an analog controller based BBU design. So this also is designed up to 7 kilowatts, uses our LM51770 as the main controller to do the design. And this again uses the same GaN FET, the LMG3100R017. So again, hits a peak efficiency of greater than 98.5%. And yeah, it can be used in a multi-phase configuration as well. Again, meets the OCP ORV3 standards and the specifications that are mentioned in the document. And last but not the least, this is the newest design. It can actually go and scale up to 12 kilowatts. This is the highest power BBU design that we have. This uses 6 phases with 2 kilowatts per phase, and uses LMG 3100R017. And it also has the scalability option further in each card to actually go to even a lower RDS on FET, which we are shortly coming out with. And that, I think, again, will hit a peak efficiency of 98.5% at an even higher power. So this actually is a very popular design now. This uses actually a very good combination of analog and digital. So it has an analog controller on each of the 6 phases, 6 BBU cards that you see. But the housekeeping for the 6 phases is done by a digital controller, which is our C2000 series controller. So it's like a design which combines the best of both worlds. And yeah, this is also now released on ti.com. With that, I'll just move to the TI GaN in intermediate bus converter, right? So we'll just talk about and again, we are focusing on Gen 2 today, 48 to 12 volt, 48 to X volt kind of scenarios. So here we have multiple topologies that we can work with. I'm gonna show you 2 of the more popular topologies, right? Where we have released designs on ti.com, right? So the first one is the buck, or the multi-phase buck. So we are using a 4-phase GaN-based buck to do the 48 to 12 volt regulated design. So this is a regulated design at 2 kilowatts. So the form factor is standard. It's called quarter brick, 36.8 by 58.4. And this can deliver a very high efficiency at around 98.1% at 1 kilowatt and 97.5% full load at 2 kilowatts, which is the full load. Yeah. So this again uses the LMG 3100R017. This can also use our half bridge devices, many of them. But yeah, for this design, we are using a R017 with our UCD digital controller, UCD3138. So this is just the different view of, or rather different cross sections of the design. If you see, we are using 2 coupled inductors, so to deliver the 4 phases, right, of the buck. And you can see on the top view that there are 8 FETs, 8 of the LMG 3100 R017 in the high side and low side. And as we come with a lower RDS on FET in the future, actually the low side FET where the conduction loss is dominant, we can replace, or we plan to replace it with the lower RDS on FET, which will give you a better number on the 2 kilowatt level. Basically, it will increase the full load and mid load efficiency at both 1 kilowatt and 2 kilowatt basically. So that's the future scalability plan. But for now, this is the design, and this has been released recently, I think, on ti.com just a day before. So the design number is TIDA050095. So all the BOM schematic, all the design files are available on ti.com now. And same goes with the previous designs, by the way. All the BBU designs that I just spoke about, all that is on ti.com with every file that you need, like schematic, layout, BOM, etc. So yeah, coming to this, just to show you the efficiency numbers, right? We have tested it in our labs, and you can see that at 40 volt, the peak efficiency at 1 kilowatt is around 98.35%. And at 48 volts, it's around 98.15%, right? Even at 54 volts, which is another burst voltage, it's almost 98%. So it is actually a pretty good design, industry leading in that way, because we have gotten feedback from many of our clients whom we have spoken to, and they have all liked the efficiency profile over here. Even the full load efficiency, which is very crucial for the GPU kind of workloads, because the step up is sudden and it is almost goes to the full load region. The full load efficiency is almost around 97.5% at the 48 volt, like at the 48 volt voltage level, and 97.4% roughly at the 54 volt VN. So this is a regulated design. It will give you a very tight regulation at 12 volt or to within plus minus 5%, and can be used to bring about your power conversion. Yeah. We also have a planar transformer based LLC design. This is an unregulated design. This is also released on ti.com. Uses our half bridge device, the LMG 2100 R044, scalable to the R026. So that option is also there, and the UCD 3138. So this design is switches at 1 megahertz. So truly gives you the switching capability. Since it's a soft switched topology, gives you the switching capability of our GaN devices. You can really go high on the switching frequency. Even the previous design was at 200 kilohertz, which is much higher than what standard silicon hard switch topologies like buck or boost switch at. So yeah. So coming to this design again, this is in a 1/8 brick format, or 1/8 brick size, 22.9 by 58.4. So really high power density, and can deliver 1.1 kilowatt at a 97.7% peak efficiency. So this is also there on ti.com. Please go and take a look. And yeah, this is the efficiency and loss curves available on the test reports on ti.com as well. So as you can see, with bias, we are hitting an efficiency of 97.7% peak. Without bias, without onboard bias, that number will be even higher. So with this, I think I'm about to conclude the presentation. Feel free to now keep asking questions, but before concluding, I would just like to show you some of the ref designs that we have in the server space, and this is a good look at that, right? We have PMP 23421, 23377, and the 41155 that I just showed. In the BBU space, in the IBC space, we have the 23340, the TIDA 050089, both at 1 kilowatt, and then the 2 kilowatt design that I just showed, the 050095. And then we have a bunch of designs in the PFC and the isolated DC-DC phase, which is for the PSU side, which was one of the other subsystems that we didn't cover in today's presentation, but is an equally important subsystem to deliver at a very high efficiency. Or deliver power at a very high efficiency. So all these designs that you see on your screen are GaN based, and this is not an exhaustive list by any stretch of the imagination. This the list is ever growing, and this already is a bigger list than this on ti.com. So please go take a look, browse around, and ask questions as well if you need, right? If you need more information, right?
Okay, thank you, Siren, for that great presentation. Audience, please remember that you can still submit questions, and they're going to be reviewed at a later date. So before we close out this All About Analog and Power live session, I'd like to announce our prize winners for the session. Congratulations to Dave Bursky and Gavin Darcy. We'll be in touch with you within the next week to ensure we have the information we need to send you all the All About Circuits goodies. And since this is the last session of the day, I get to announce today's grand prize winner. Congratulations to Daniel Swevland. You are our lucky grand prize winner. Our All About Circuits event team will be reaching out to you to make sure that you can select the prize that you truly want. In just a moment, you're going to be redirected to Texas Instruments Summit Series microsite. I encourage all you to check out other live sessions, keynotes, and published content for our month-long virtual event. So I want to thank the speaker and thank all you audience for attending All About